What if computer code didn't just run on a machine? What if the code actually was the machine? Today we're going to dive into a pretty radical concept called biosemantic computation. It's an idea where information doesn't just get processed, it literally builds itself into something real. I mean, think about it. Every program you've ever used, the output is always just data on a screen, right? Some text, an image, a number. But what if the output wasn't pixels? What if it was a real physical thing, a structure that has its own function, created directly from the code itself? That, right there, is the wild idea we're exploring. So, to even begin to understand how code could build an actual object, we have to zoom all the way in. We need to start at the absolute smallest scale and look at the fundamental atom of this entire system. And that fundamental unit, it's called a codon. Now, in the computers we use every day, data is just passive. It's information that sits there until an instruction comes along and does something to it. But in this system, the codon smashes all of that together. The data, the instruction, and its meaning are all one and the same thing. The information is the action.
Okay, let's make this real. Here are just a few examples. Out of 64 possible codons, each one acts like a powerful little verb. So ATG isn't just data, it is a command to create. CCC is literally an instruction to lock down and stabilize the system. Every single one of these is a direct, meaningful command that physically changes what's happening.
And this is the fundamental shift. On the left, that's our current world, passive data waiting for instructions to tell it what to do. But on the right, you've got the biosemantic model. The codon is the data, and it is the instruction. There's no separation at all. And that simple change, well, that is the engine that drives everything else we're about to see. All right, so we have these powerful individual units, these little verbs, but single words don't build a cathedral. To create something really complex, you need to string them together into a coherent set of instructions, what we can think of as a chain of command.
Exactly. A single codon is like a word. It's got power, sure, but the ability to tell a story, or in this case, to build a machine, that comes from stringing those words together into a meaningful sentence, a sequence.
So how does the system actually read this sequence? It uses a method inspired directly by biology's own ribosome. It's pretty straightforward. It reads the very first codon in the chain and physically changes the system. Then it just moves to the second codon and changes the new state. It's a step-by-step process where each instruction builds directly on top of the last one. Now, this process has some very strict, very important rules. First, the order of the codons is absolutely everything. You swap just two of them and you get a completely different result. Second, each step permanently changes the system, and that creates a one-way path of transformation. There is no undo button. You can't go back. And this one-way path, this irreversible process, leads to the most incredible part of this entire idea. What actually happens at the end of the sequence? Well, this is where the abstract process of computation becomes a physical, functional structure. This quote right here just nails it. The system doesn't return a value. There's no print statement at the end. The computation doesn't tell you something. It becomes something. The final output is the system itself, completely transformed into a new physical state. So what does it become? Well, the final step is called folding. And just like with proteins in our bodies, it's all about shape. Once that entire sequence has been read, that chain of commands forces the whole system to basically collapse on itself, settling into a stable, final form. And that shape, that is the function. And here is the real payoff. You don't program the final function directly, it just emerges. It's a natural consequence of the sequence you fed it. The physical laws of the system itself figure out the most stable shape, and that shape determines its purpose. The code literally builds its own function into existence. So let's recap. We've got codons that form sequences, which are then read to create these folded functional structures. But wait, where do all these powerful sequences, these blueprints, even come from? That brings us to the system's foundational library. The answer is something called the genome layer. You can think of it as the master archive, the complete library of every possible codon sequence the system can use. It is the deep repository of all potential forms the system could ever hope to take. So here you can see the whole shebang from start to finish. It all begins with the genome, that library of possibilities. A specific sequence gets selected from that library. The ribosome then reads that sequence step by step, transforming the system. And finally, that whole chain of transformations folds into a unique functional structure. It's a complete journey from abstract potential all the way to physical reality.
So let's pull all this together for a second. What we've just described isn't just a new programming technique. It is a profound, fundamental shift in what we even consider computation to be.
On the left, you see traditional computation. It's basically a linear factory line. You put something in, it gets processed, and you get an output. But on the right, you see biosemantic computation. It's not a line, it's a generative cascade. A sequence creates a transformation, which folds into a structure, and that structure is the function. It's a deep shift from calculating answers to generating reality.
And this quote boils it all down perfectly. The goal of this kind of computation isn't to calculate an answer, it's to form a structure. Computation stops being about processing symbols and starts being a creative act of building. Ultimately, what this does is reframe computation as morphogenesis, which is just the fancy biological term for how living things develop their shape. We are no longer just manipulating abstract symbols in a vacuum, we are using information to generate real, tangible form and function in the world.
And it's important to mention that this entire fascinating framework, from the codons all the way to the folding, was developed by the researcher Luis Ayala KPK, really pushing the boundaries of what we can even imagine computation can do.
Which leaves us with one final, pretty massive question to chew on. If information can learn to build its own physical structure, to literally manifest its own function in the world, what does that mean for the future of artificial intelligence? What happens when our software can actually grow itself?